Okay, today we're going to be talking about chemical sedimentary rocks, which are some of my favorite rocks. Our goals for today are to differentiate between biochemical and chemical or abiotic sedimentary rocks, briefly introduce carbonate chemistry, describe the chemical significance of banded iron formations in Earth history, and start to use the Dunham and Folk classification schema to name carbonate lithologies. Okay, so first just starting with how you identify chemical sedimentary rock from a clastic sedimentary rock, or how to differentiate them. So next time, and in many of the next lectures, we're going to be talking about clastic sedimentary rocks, but today we're talking about non-clastic. So clastic or detrital rocks, these fall into a couple of different categories. You can have volcanoclastic, so these are reworked volcanic minerals like tuffs, which are ash. Terrigenous clastic, so these are your mud rocks, your sandstones, your siltstones, your conglomerates, the typical, siliciclastic grains. Then you can have carbonates, which can be clastic or non-clastic. Typically, they're chemical or non-plastic, and that's what we'll talk about today. You can have other chemical rocks such as coal or ironstones or phosphorites or cherts or siliceous deposits or evaporites. So in this lecture, we'll be talking about chemical sedimentary rocks as opposed to clastic sedimentary rocks that we've primarily discussed up until this point. So clastic rocks like sandstones and mudstones are formed of clasts that are transported to the depositional environment, whereas chemical sedimentary components are transported as ions in the solution. Like you can have dissolved sodium or calcium, carbonate, and so on. The key here is that chemical sediments precipitate from solution rather than originating as a piece of an igneous or metamorphic rock. So we won't get deeply into the chemistry of chemical precipitation in this course. If that interests you, you should reach out and I can share lecture videos from the carbonated geochemistry seminar that I teach every other fall, or you're welcome to take that course. So each chemical system has its own components, and components and constants that set the behavior of precipitation. But because limestones are an important chemical sedimentary rock, we'll use carbonate as the system as our example. So the components of the carbonate system, there is carbon dioxide or CO2, bicarbonate or HCO3 minus, carbonate ion CO3 2 minus, hydrogen ion H plus, and hydroxyl ion OH minus. So when a system is in chemical equilibrium, all of the different components can be related by equilibrium constants, which are given by the capital letter K. The first basic principle is Henry's law, which states that the amount of dissolved gas in a liquid is proportional to the partial pressure above the liquid. So this can be applied to the ocean, where the dissolved CO2 in the surface ocean is in an equilibrium with the partial pressure of CO2 in the atmosphere. And the constant is K naught. This is the solubility coefficient, which relates two phases of the same species, but in different phases. So we can draw this out. So when CO2 of the atmosphere is in equilibrium with dissolved aqueous CO2, this arrow is showing that equilibrium, that K naught solubility coefficient between the two phases of CO2. So now what I'm showing you is what's called a Bjerrum plot. So this is a plot relating the concentration of a dissolved species and the pH of the solution. So here on the x-axis, you have pH going from 0, so very acidic, to 14, or very basic, and then the log of the concentration of your species. So the way to read this is dissolved CO2 has a log concentration of, maybe about negative 2.7, at a pH range of 1 to maybe 5, and then it starts to tank, and it really goes down quickly. At that time, bicarbonate concentration increases, and there's this point where the two cross, where they're in equal proportions, and then bicarbonate becomes more dominant. Same thing happens as you increase pH further in your solution. Your bicarbonate will start to tail off, and your carbonate ion will start to dominate. So we can draw a line on here at the pH of surface oceans, about 8.2, and we can see that the dominant carbonate species is bicarbonate because it's in the highest concentration here. Following this line down further, next is carbonate ion, and then way down here is where it intersects with CO2. Now we can start to pose a hypothesis. So if we hypothesize that oceans are becoming more acidic, let's say it reaches a pH of 7, how does the proportion of dissolved CO2 versus carbonate ion change? So you would do the same thing, where you would look to see where that line at pH of 7 intersects with the CO2 concentration and the carbonate concentration. And you can see that now CO2 is in greater abundance than it was at ocean pH, and carbonate ion, on the other hand, is much lower. So they've sort of swapped roles here. Now, what would happen if we were in an alkaline lake that, say, had a pH of 10? So at that pH, your carbonate ion is going to be in greatest proportion. So you can do these same sort of exercises with similar plots for different dissolved species. So for example, we have iron speciation over here, we have phosphorus speciation, and silicon speciation. Okay, so those are the conditions under which different ions will dominate the system, which helps us understand what minerals are likely to form in different solutions. So next we're going to talk about the different types of chemical sedimentary rocks that form from these solutions. So limestone is by far the most common chemical sedimentary rock. This is what I typically study. Chert, this is dominantly silica. Banded iron formations are a unique type of rock. I just am including that as an example of how chemical sedimentary rocks are used to understand Earth history. And evaporites typically form in chemically closed basins by salt formation. So let's start with chert first. So cherts typically form by compaction and recrystallization of silica-rich biogenic sediments that are made up of what are called silicate tests of single-celled organisms like diatoms and radiolaria, or remains of siliceous sponges, which you see over here. These are all microscopic images of these sponge spicules and diatoms. So thick beds can form in deep marine environments from dissolved silica or piling up and reworking of these siliceous biogenic materials. They can also be found as nodules or concretions within limestones, banded iron formations, or cryptocrystalline quartz. So primary chemical chert formation, when it's not necessarily diatoms or sponge spicules that the silica is coming from, these form when dissolved silica particles flocculate, which is what you see over here on the left, where these are bonding together in solution. So the silica particles will flocculate with the aid of positively charged hydroxyl complexes. So you see these OHs. This happens in the water column. The dissolved silicic acid, so you see H4SiO4 over here. The acid will adsorb onto settling particles like the silicate, and on the seafloor, the siliceous ooze that accumulates becomes cemented by the concentrated dissolved silica until eventually you get a clastic-rich chert. It's plastic-rich because it has these silicates in it. Another unique but key diagnostic chemical sedimentary rock type in the rock record is banded iron formation. So banded iron formation, or BIFs, are interbedded layers of cherts and iron-rich silica-poor sedimentary rock. So what is so key about this rock type is that the oxidation of iron, as seen in the bright red layers in this lower left example, indicates an oxygen-rich atmosphere. So these types of rocks were not present in the rock record prior to the oxygenation of the atmosphere, so it allows us to put a date on the event. On the right, I have a figure from a somewhat recent paper that reviewed the popular models of formation of BIFs. So an early model suggested that banded iron formation sourced iron from riverine runoff. The newer models suggest that iron was sourced from hydrothermal vents, so coming from that deep sea hydrothermal heat cycling that I talked about in the past unit, and biologically cycled iron too by dissimilatory iron reduction in coastal sediments. So here I'm just showing you on different scales, so at the outcrop scale, hand sample scale, and thin section scale, or microscopic scale, what these alternating layers of chert and iron oxides look like. So banded iron formations, as I said, can be used as an indicator of oxygenation. So showing you this paper, Johnson 2018. Oops. The upper panel here shows what we think we know about the atmospheric oxygen levels or concentration relative to present atmospheric level, where this is the modern, and we're going back in time this way. So our atmospheres were anoxic in the Archean. Ocean oxygen level is given on the right-hand y-axis in blue. So we have evidence from mineralogy of very, very low levels of oxygen in the oceans in 3.5-ish billion years, and we start to see a slow rise in the levels of oxygen, whereas the atmospheric oxygen, we maybe had some small whiffs or pulses of oxygen between 3 and 2.5 billion years ago, but then there seems to be sort of a relatively sudden rise in oxygen, and this is called the GOE, or the Great Oxygenation Episode. In the lower panel, you see abundance of iron formations in the rock record. You can see that today, and really for the whole Phanerozoic, the last 540-ish million years, there have been no banded iron formations in the rock record. And this is because our Earth's surface is fully oxygenated. But there are periods in Earth history, in the Proterozoic, and for sure in the Paleoproterozoic and the Archean, where you get much greater abundance of these reduced iron formations prior to that GOE. All right. And now thinking about my favorite type of rock, carbonates. It's very common. It makes up about 1/5 of all sedimentary rocks in the rock record. It's been found on Earth for, about 3.5 to 4 billion years of Earth history. It can form totally abiotically, chemically, or biology can be completely central to its formation. So limestones, again, they're extremely common in the sedimentary record. They can form totally abiotically just from supersaturation of carbonate, or biology plays a huge role. Here you're seeing a fossiliferous or a biochemical limestone. So you can see there are what are called bioclasts, which are fragments of biological origin, such as shell fragments and fossils. These are the common grains that you find in limestone rocks. It's really the only type of grain you'll find is if there are shelly fossils. Limestones can also form directly by chemical precipitation. So here you're just seeing sort of like a lime mud. These are pictures that I took at Mono Lake in California, which is a hyperalkaline lake. Because it's hyperalkaline, carbonate forms abiotically here. So here you see pebbles from a fluvial input that are just cemented together by carbonate. These are tufa towers. So these are carbonates that form by supersaturation along the shorelines. But you can also get beyond just shells and beyond abiotic chemical precipitation, you can get chalk that forms. So chalk, which we've all seen and probably touched and used, that powdery rock. This is a marine limestone that's formed entirely from tests of microscopic algae and foraminifera. So this is an image of the cliffs of Dover, which are made of chalk. They form much of the coastline of the UK, and they're the remnant of tiny marine organisms that lived in warm seas 70 to 100 million years ago. So if you were to take a chunk of the chalk that makes up the cliffs along the United Kingdom shorelines and throw it in a scanning electron microscope, this is what it would look like. So these are coccolithophores. These are them when they're kind of broken up. Another way that biology can mediate carbonate production separately from it being like a part of their body, like the coccolithophores or shells, are microbial metabolisms. The microbial mats, they've been around for over 75% of Earth's history. Over the last 2 billion years, cyanobacteria, so these are photosynthesizers, they influenced evolution by releasing oxygen in the atmosphere, driving the Great Oxygenation Event, but they also cycle alkalinity and dissolved inorganic carbon and can mineralize to form these carbonate structures within microbial mats. There are two different schemes for categorizing carbonate rocks. The two main schemes are Folk and Dunham. So Folk on the right here, you can see this chart. It's primarily answering two questions. What is the matrix or cement made of? And what are the components or the allochems? So for example, if you have more cement, you see sparry calcite cement, you can see it's drawn with this blue sort of crystalline material between grains. Or you can have micritic matrix, which is carbonate mud, that just sort of fills in the spaces between grains. So just as a little practice, I'm going to pause after I ask these questions so you can have maybe 5 seconds to figure out what the answer is. So what would you call a rock with a micritic matrix and peloids? So if it has a micrite matrix and pellets or peloids are the allochems, it would be a pelmicrite. So what would you call a rock with sparry cemented shells? Sparry cement and fossils, it would be a biosparite. What would you call a rock with sparry cemented pieces of other carbonate rocks? Intrasparite. So the other classification scheme is the Dunham scheme, and this is most comparable to the classification scheme that you'll use for categorizing clastic sedimentary rocks, because you describe the component types, the sizes of those components, and the quantity. So, for example, if it's mud supported, if it's less than 10% grains, it's a mudstone. So the primary thing you're thinking about is how much of it is grain versus matrix or cement. So if there's no recognizable texture and it's just crystalline, then you just have crystalline carbonate. If the components are bound together during deposition, it's typically microbial or organic. It's going to be called a bound stone. Everything else has sort of a more clastic scheme. So if all of the grains or allochems that make up the rock are touching, so it's grain supported, there's less than 10% mud, and it's called a grain stone. If the grains are mostly touching, but there's more than 10% mud, it's called a pack stone. If it's more than 10% grains, but it's matrix supported, so you can see none of the grains are touching, it's a wax stone. And then if it's less than 10% grains, it's a mud stone. So the last type of chemical rock I want to talk about are evaporites. These form in hydrologically and chemically restricted basins, so typically like lagoons or shallow playas or lakes. For example, Death Valley, as seen here, which is seasonally floods and then evaporates away. So salts and ions are carried to these shallow, restricted basins by rivers. And then as water evaporates from them, there's nowhere for them to get more water or to lose water by streams leaving the lake. So evaporation is the only way that water leaves. As water evaporates, the salt does not evaporate. It stays in the basin, and so it precipitates out as a mineral and forms these salty crusts. So you can ask, what would happen if you evaporated the oceans? So you can figure out what the composition of seawater is, and then figure out what would happen if you precipitate 50% of it. The first thing that would evaporate out would be calcium carbonates. If you precipitated 85% of it, then gypsum, so those calcium sulfates, would precipitate out. If you precipitated another 5%, then you'd get halite. And then another 5%, you'd start to get potassium and magnesium salts. If you precipitated the whole column of seawater, or if you precipitated 1 kilometer of a column of seawater, you would get 17 meters of evaporite minerals, which is very thick. And it would be mostly halite, so sodium chloride, a teeny tiny bit of calcium carbonate, 3.6% gypsum, and 17.6% potassium and magnesium salts. Okay, the last thing you're going to do is log into TapHat, and there's a question that's open for you. Is a short answer, and you just have to answer, what would you immediately know about the ancient environment if you found banded iron formations in an outcrop?